attention, or you can be seeing to your hair in preparation for the photograph. I'm really very grateful to the organisers for inviting me to this meeting. It's been most interesting to see the developments in the field of quantum information, not my field, but one that I take a distant interest in. So I found that really extremely inspiring. What the organisers have asked me to do is to give 2 lectures as some sort of summary or overview of random matrix theory. Now we've already heard random matrix theory plays a key part in thinking in quantum information theory, and there are others far more expert than I am in explaining exactly how that thinking has developed. Rather, what the organisers have asked me to do is to give an overview of the classical structure of random matrix theory, with a view, I think, to stimulating thinking on whether there are other problems or other ideas in random matrix theory that may play a role in quantum information theory. Now, one of the key parts of random matrix theory, which is a huge subject, by the way, a subject that's nearly 100 years old, been intensively studied for the last 50, 60 years at least. One of the key issues of it is that there are many, many, many connections to other areas of physics and mathematics. And this has made the subject extremely exciting in the last few decades. So I will try to mention those as well. So I have 2 lectures which are meant to survey 100 years of development in random matrix theory, and I feel I must also include some of the connections to some other areas of physics and mathematics. And so these 2 talks will by necessity be very considerably more superficial than those that have gone before in the workshop. Rather, my purpose will be to try to fly over the mountain range and simply draw connections between different ideas. Some of them I may only mention in a sentence or 2, but the hope will be to give you some feeling that random matrix theory sits at the centre of a very large web of ideas and connections, and some of those may be useful to you, or rather, some of those may have problems that you feel you can solve with the techniques that have been developed in quantum information theory. So to sort of schematically set this out, the way I see it is that random matrix theory has connections that we've been hearing about to quantum information theory, and we've already had some very beautiful lectures on that. So I shall take that connection as given. And rather what I'd like to do is to give you some feel for some of the other techniques and ideas that in random matrix theory that I'm not sure have yet made their connection with quantum information theory, but also to flesh out for you, really quite superficially, some of the other connections between random matrix theory and other areas of mathematics and physics, so that then you have at least some feel for how quantum information theory, through random matrix theory, connects to those other areas. And maybe this is a sort of landscape to be explored in the future. So I'll start with a sort of history and a context, just to sort of get some momentum up. So quantum mechanics, of course, was created as a linear theory and was expressed in its very earliest incarnation by Heisenberg in matrix form. So it's natural that matrices play an absolutely foundational part in quantum mechanics. The issues arose in the 1950s, primarily in the field of nuclear physics, where one deals with complex quantum objects, nuclei, often heavy nuclei with many interacting nucleons, where one has to ask what are the properties of complex quantum systems. And the idea was developed by Wigner in the 1950s that perhaps one should view this in the same way that in the 19th century people viewed the development of classical statistical mechanics. So in classical statistical mechanics, one takes given deterministic law of motion, Newton's equations of motion, perhaps for the particles in the gas around in the air around my head, in principle, one can solve the equations of motion. But in practice, that would be futile because one doesn't actually want to know the detailed information about where each gas particle is moving. Instead, one's much more interested in statistical properties. So, for example, what's the average temperature, or what are the fluctuations in the temperature or pressure? And for that, one can derive those gross statistical properties from the equations of motion with some assumptions, sometimes provable, sometimes not, of statistical behavior in the solutions of Newton's equations. For example, ergodicity, that gas particles are equally likely to be moving in any possible direction. One can, from that assumption, as Maxwell and Boltzmann did, derive statistical properties of the gas. And this was Wigner's insight that perhaps one could view quantum mechanics in the same way. So for a complex quantum system, where one in principle can write down the Schrödinger equation, that is, one has a matrix that in principle one could write down, a matrix that would incorporate the information about the forces between the nucleons within a nucleus, that perhaps one could write down, one could analyze that statistically by embedding that one Hamiltonian, the Hamiltonian for a given nucleus, within a family of Hamiltonians, and then asking for statistical properties of that family. And hopefully, and it turns out provably, one can say something about typical quantum Hamiltonians, typical quantum matrices, by embedding them within a family of quantum matrices, averaging over that family, and then proving some notion of ergodicity, that for matrices with certain properties, now I'll set this out later, one can prove that, particularly for large matrices, any given large matrix is almost surely the same as behaves in almost surely the same as an ensemble average. The ensemble averages can be computed, and so one can say something about statistically about the statistics of large complex quantum systems. So this was Wigner's motivation. So I'd put this as complex quantum systems. So Wigner set out this vision and did some calculations in the 1950s. In particular, he proved something like the Marchenko-Pasteur law. I'll make that precise later into what I mean by that, for matrices that were within the class he wanted to study. And then in the 1960s, the subject was taken up by Freeman Dyson in particular, but Godin and Mehta and many others, who established this as an area, a systematic area of rigorous mathematical physics. So basically, they showed how to calculate pretty much anything for a certain class of matrices. And this was enormously influential because basically they identified a set of problems in random matrix, or a set of types of random matrix for which one could calculate anything. So these are, if you like, the kind of simple harmonic oscillators of the subject. They're exactly solvable problems where one can calculate anything. Then one can go on to ask about perturbations of those problems, or whether those problems are typical of a wider class. And in some cases, one can prove that they are. So that's how the subject developed. In the 1970s, it was realized that one didn't need large numbers of interacting particles for random matrix theory to apply. So Wigner's imagination, or Wigner's vision, was that random matrix theory would apply in systems with a large number of degrees of freedom, with many strongly interacting particles. But it was realized in the 1970s that in fact one could get away with very few degrees of freedom, and this is the subject of quantum chaos. So in particular, as an example, if you solve Schrödinger's equation in a domain of this shape, or a domain of this shape, the dynamics would be a particle bouncing inside such a domain, making specular reflections at the boundaries. Schrödinger's equation in these cases is very simple. So that in each case there's one particle moving. Schrödinger's equation is very simple. It's just a Helmholtz equation with appropriate boundary conditions, for example, Dirichlet boundary conditions. It was understood that the high-lying states of these systems and other systems like this, where the classical dynamics is chaotic, would also be governed by random matrix theory. In the 1990s, it was realized, for a completely separate set of reasons, that random matrix theory also plays a foundational part in quantum gravity. And string theory. Right, so the program there was to develop models of quantum gravity or string theory that are exactly solvable, and it turns out that random matrix theory supplies those models. So there are calculations that you can do in random matrix theory exactly, which solve certain discrete models of quantum gravity and string theory. And I'll say more about that if I have time tomorrow. So these areas of physics are very intimately related to random matrix theory now. In the 2000s, there was developed a connection with more general areas of quantum field theory. When it was realized that random matrix theory can be re-expressed as a quantum field theory, which again is exactly solvable field theory. So that has been a major part of a major strand of research. So those are the areas of physics that, some of the areas of physics that random matrix theory has appeared in. But there are many areas of mathematics as well, and I'll touch on some of these, I hope. We've already heard in the beautiful lectures on free probability of connections with random permutations. So we've seen in those lectures that some calculations in random matrix theory can be re-expressed in terms of counting certain partitions restricted in a certain way. And the way that was expressed was that one can do calculations within random matrix theory by counting those partitions. But in fact, there's a much more wider class of problems where one wants to count certain objects, for example, counting the longest increasing subsequence of random permutations. So you take the numbers from 1 to n, you make some random permutation of them, and then you ask what's the longest increasing subsequence that one can find within that string of numbers. There are many other problems like that. Where it turns out that in those cases one doesn't know the answer a priori, but one can make a connection with random matrix theory. One can calculate the random matrix quantity using other techniques, and so that provides an answer to these questions that one can ask about random permutations. The same holds true for what one might call enumerative geometry or topology. And I may have more to say about this tomorrow. It turns out that there are some quantities one wants to count, certain types of knots, certain types of graphs, where one can establish that the quantity you want to count is related to an integral over a space of matrices. If you have a separate method for computing that integral, that then provides an answer. And in recent years, that's been an extremely active area of research, has been to count quantities by relating them to random matrices, computing the random matrix integrals in question by other techniques, and so providing an answer. Historically, the random matrix theory arose, as has been mentioned actually, before Wigner in two, at least to the best of my knowledge, two separate ways. And I think it's worth saying a little bit about that because, well, it's interesting. So as I know, the first ensemble of random matrices were those that we've been hearing about in the lectures on free probability. These are the Wishart matrices. And these arose first, not in quantum mechanics, not connected to beautiful abstract ideas like free probability, but an attempt to understand agricultural data. This is really rather practical. The idea was that one has, this is due to Wishart, so John Wishart, in 1928. He worked at the Rothamsted Agricultural Research Station, so he wasn't in the ivory towers of academia. He was off really working with people doing experiments in agriculture. And the generic problem that he came up with was the following. You have some quantities which are labeled by different populations, n. So, for example, these might be different populations of animals. These might be different populations of plants. And you sample that population at various times t. And what you'd like to know is, what are the correlations between different populations on average over time? So you'd like to compute something like Qn, Qm, and this is something that in statistics is called the empirical correlation matrix. So we can denote this ENM. And this plays an absolutely foundational role in statistics. It's one of the basic building blocks of statistics. You have these different species, different interacting environments. You can sample them at certain times, and you want to work out what the correlations are, whether there are any. Well, what you can re-express this if I write QNT to be x over root t to be x and t. And this is just x, xtn. This will be xtn x transpose x. So if we take these populations to each have a normal distribution, then the matrix elements of x have a normal distribution. And if we assume, for example, that they have a unit variance, or, this would form the Wishart ensemble of random matrices. So the problem Wishart wanted to understand was what the distribution of the matrix elements of this matrix would be if the matrix elements of x itself came from some multivariate normal distribution. This, of course, has now many other applications. In fact, some of the most interesting applications of random matrix theory currently, or some of the most profitable, come from the finance sector, where one might take these QNs to be the price of different stocks, stocks labeled by n, sampled at various times t, stocks evaluate the value of certain stocks calculated once every week or something like that, and you want to know whether they're correlated or not. And it's no surprise, or no accident, I should say, that one of the largest hedge funds in France is currently managed by one of the most distinguished random matrix theorists that France has produced in the last few years, who was at the École Polytechnique, still has a position there, who has a team of people working on applying random matrix theory to understanding correlations in the stock exchange. So I can put finance here, although I'll have that dotted line there since I don't properly understand that. The other area that random matrix theory sprung from was numerical computation. And I think here there may be connections to problems that might interest people in this community. And this was an observation of von Neumann. If you want to solve, this is one of the basic problems of numerical linear algebra, you want to solve AX equals B, where X is a vector, B is a vector, and A is a matrix. Well, we know how to solve that if A is invertible. But numerically, you might want to ask the question, if you only know B imprecisely, how does that imprecision in your knowledge of B transfer to an imprecision in the knowledge of the solution X? So this is characterized by the what's called the condition number of the matrix A, which is the ratio of the largest to the smallest singular values of A. So if A is a square matrix, this will be the ratio of the largest to the smallest eigenvalues of A. So there's the condition number. Von Neumann actually had to solve these problems, and in the 1940s, you can imagine why he was solving them in Los Alamos. It was intensely time-consuming to do these computations. It involved hundreds of people. So von Neumann wanted to understand how reliable the computations would be. So he wanted to know what the size of the condition number would be of a matrix that was presented to him from some calculation that someone wanted to do. So he asked the question, I think it's completely independent of Wishart, what would be the condition number of a random matrix? And would that condition number of a random matrix, in some sense, tell him about condition numbers of typical matrices that he was presented with? So von Neumann asked this von Neumann posed the question, and in fact did quite extensive numerical computations. So von Neumann actually did some numerical random matrix theory. He would generate random matrices, work out the condition numbers, work out the distribution of them, and he came up with a sequence of conjectures in the late 1940s and early 1950s with Goldstein, which were actually solved in the late 1980s using ideas from random matrix theory. So actually, it was shown that one could calculate the distribution of condition numbers analytically using properties of the Wishart ensemble of random matrices. So I think that completes what I wanted to say, some sort of background. I want to give you a feel that random matrix theory touches on many different subjects, and people have come to it from a whole variety of different directions, but what one sees now is that it's an organizing principle connecting all these subjects. And I repeat, my hope in doing this was to give you a feeling that in the connections between quantum information theory and random matrix theory, you're actually connecting not just to random matrix theory, but to also all its many friends. So now let me get down to what random matrix theory is. We've already had some examples. In particular, the Wishart ensemble has been discussed, but I want to give some other examples and discuss the classification of them. So random matrix theory, what is it? It's a space of, the canonical setup is that you have a space of matrices X, with a probability measure P of X. And these might be finite matrices. One might want to consider the limit of matrix size tends to infinity, whatever. So what are the possibilities? Well, there are various different strands of random matrix theory. Perhaps the earliest examples that were studied would be matrices associated with classical compact groups. So example 1 would be where the matrix X is an element of the unitary group UN, or the orthogonal group ON, or the symplectic group SP2N. Each of these groups comes endowed with a natural measure. It's a measure that's invariant under the action of elements of the group. That's the Haar measure. And so one can ask, what are the properties of a typical unitary matrix, or a typical orthogonal matrix, or typical symplectic matrix, by which one means drawing a matrix at random uniformly with respect to Haar measure on the group, and then analysing the distribution of its eigenvalues, for example. So in this case, the eigenvalues lie on the unit circle, because these are all unitary matrices. And in the case of unitary matrices, the eigenvalues can lie anywhere on the unit circle. And in the case of orthogonal and symplectic matrices, the eigenvalues come in complex conjugate pairs. So one has a symmetry in the spectrum. So these are what one might think of as invariant ensembles, an example of an invariant ensemble, because the probability measure is the measure that's uniform with respect to, by definition, uniform with respect to actions of elements of the group. So one can also ask for whether one can generalize this or extend this to, for example, Hermitian or symmetric matrices. So we might take X to be real symmetric, or complex Hermitian, or even quaternionic. So we want the elements to be X, N, M, N is X, N, M, or X, M, N is X, N, M, complex conjugate in that case. And then one can ask about a space of such matrices, perhaps of dimension n, square matrices, where the probability measure in the first case is invariant under the action of matrices which diagonalize X, so orthogonal matrices. And in this case, the measure, the probability measure would be invariant under the action of matrices which diagonalize Hermitian matrices. These would be unitary matrices. So these ensembles are like those I've described above, in that one has a probability measure that's invariant under some action, and these are called invariant ensembles. If you take quaternionic matrices, then one would just have invariance with respect to symplectic transformations, but they play less of a role in what I want to say. The third class would be what are called Wigner random matrices. These are the ones. So again, X might be real symmetric or complex Hermitian, but we might simply want to take X, M, N to be independent random variables. Say mean zero and unit variance, whatever you like, and the elements X, N, N that would be real independent random variables, probably identically distributed just to make this well behaved. So these matrices form an ensemble which are not invariant in general. However, there is one class of matrices which play an extremely important part in random matrix theory, which are at the intersection between 2 and 3. So there's one particular choice of ensemble of matrices which are both invariant and Wigner, and these are the Gaussian ensembles. So if we take the probability measure, Px, to be proportional to e to the minus some constant times trace x squared, in that particular case, clearly the probability measure is invariant, but it also happens that it's, the matrix elements are independent. So this is the unique choice of ensemble which is both Wigner and invariant. And these are also called Hermite ensembles, for reasons I'll get to in a minute. And then there's a class of matrices which we've heard about already in several lectures, and these are Wishart matrices, which are where we take X transpose X. X needn't be a square matrix, but we form X transpose X. This now is a square matrix, and if we take the elements of X to be independent and, well, historically the first thing that was taken was Gaussian, you end up with what's called the Wishart ensemble. We've heard about that already. And sometimes these are called the Laguerre ensemble. And there's another class of matrices which I won't define here because it'll take me a little time, and I can use these as sufficient examples. There's also a class which is called the Jacobi ensemble. And this gives a clue about why random matrix theory is in some sense an exactly solvable problem for certain choices of ensembles. These are related to the classical sets of orthogonal polynomials. So I'll make that clearer a little later. So now you can ask, can I continue with this classification? And the answer is yes. I mean, there are all sorts of different random matrices you can come up with. But in terms of the original goal or vision of random matrix theory, everything's here already. So there are special circumstances, and I happen to think this is where quantum information theory may give rise to some very interesting questions in random matrix theory that lead to definitions of new ensembles. But in terms of Wigner's original vision, this is all there is. So there was a paper in the 1960s by Freeman Dyson who said basically that the Gaussian orthogonal ensemble, so the orthogonal invariant, U invariant, and symplectic invariant ensembles are all one needs in physics. In the 1960s, of course, it was popular to think in semi-mystical ways, and he termed this the threefold way. So there were three ways that random matrix theory could go that would cover all of physics. Tell you what he meant by this. If you want to write down ensembles of matrices which keep invariant the basic structure of a quantum Hilbert space, for example, the value of an inner product, then these are the only possibilities. You classify them in the way that you classify the Lie groups. However, it was realized in the 1990s that there are problems in physics where the Hilbert space might have some additional structure. And this was a realization due to Martin Zernbauer, actually announced in this room in 1997. He realized that some problems in physics, one has not only the inner product as a structure defining a Hilbert space, but in some problems one has some extra symmetry. For example, in relativistic quantum mechanics, one has the chiral symmetry of the Dirac equation as an additional essential structure that one would want to preserve in a random matrix ensemble. In superconductivity, so that's the symmetry. The chiral symmetry is the symmetry between particles and antiparticles. In superconductivity, one has the symmetry between particles and holes. So if your basic structure is a Hilbert space, Dyson was right. But if you're allowed to put some extra structure on, which technically then leads you to something called a Nambu space, you have extra cases. But those extra cases turn out to be just those covered by the classical compact groups. So the orthogonal group and the symplectic group. So actually, once you have the invariant ensembles that I've defined here and these cases here, you've covered everything. Now, I think it's a very interesting question as to whether there are classes of quantum problems not imagined by Dyson or Zirnbauer, but natural within the quantum information community, where there are other structures one might want to preserve. And so that would lead one to define other ensembles of random matrices. But I'll perhaps leave that as a thought for you to mull on. So given all of that, what is random matrix theory? Well, I'm going to give you some examples. I'm going to do some calculations. Essentially what it is the sort of mathematics that one already knows and loves. Mathematical physics is, to some degree, is identifying exactly solvable problems, finding a way to solve those problems, and then determining whether those solutions to those particular problems tell you about more general classes, either by perturbation theory or by arguing that those solutions, in some sense, typify a wider class, some notion of universality. Well, random matrix theory is the same, but it extends quite dramatically the class of exactly solvable quantum problems. So it's going to be a class of integrals that you can do, or differential equations that you can solve exactly, which then will tell us about a wider class of problems. So I think bear that in mind when I'm talking. I'll try and draw attention to that again. But at the heart of random matrix theory is that there are some very interesting quantum calculations you can do exactly for reasons related to integrability. So that's the end of the sort of pseudo-philosophy. Now let me get down to giving you a list of some of the results that have come from random matrix theory and talking a little bit about those. So the first would be the sort of what you might call the eigenvalue density. Now, I was going to talk at some length about this, but I've been somewhat upstaged by Ion, who gave beautiful lectures on the Wishart ensemble, the eigenvalue density there, which is the Marchenko-Pasteur law. So I decided I'll drop that because you've already heard it and it's been explained beautifully. But I will give you another variant of the Marchenko-Pasteur law, just for a sense of comparison. And this is the one originally due to Wigner. So this is the Wigner semicircle law. So the idea is you take a Wigner random matrix, that's a matrix that's either real symmetric, complex emission, could also be quaternionic. You take the matrix, the independent matrix elements to be independent random variables, as I indicated previously. And then you form the empirical measure. So these are matrices of dimension n. X will be n by a matrix. And the empirical measure, which I'll denote these lambda n's are the eigenvalues of the matrix X. And where one normalizes by square root n. Because this turns out to be the normalization that gives a nice limit. And the theorem, which is proved exactly along the same lines that one proves the Marchenko-Pasteur law, is that this random measure converges to a non-random measure in the limit as n tends to infinity, converges in a weak sense to a measure which is 1 over 2 pi normalization So if you like, if you histogram the eigenvalues, they have a semicircular density. So the spectrum has edges at plus or minus 2. That is, with extremely high probability, there are no eigenvalues beyond 2 or before minus 2, and the spectrum is denser in the center, and there are edges to the spectrum. And this theorem was proved by Wigner originally. He proved it. We now understand this holds true almost surely. He proved it for convergence in probability using the methods that Ion identified, which are the moment method. So you compute trace x to the n for various powers of n, and then you invert the moments using the Stilts's transform to deduce the underlying measure. So this holds true for all Wigner matrices. So whenever the elements are independent, it also therefore holds true for the Gaussian matrices, the Gaussian ensembles. And in that case, one has a completely independent method of proof, in fact, several. I'll identify what that independent method of proof is in a moment or two, if I have the time. But for the Gaussian ensembles, one can establish this result, but also one has an exact formula for any matrix size, and one can establish the rate of approach to the limit and the nature of fluctuations around the limit very precisely. Now, this is important because for the sort of philosophical reason that I mentioned earlier, the proof that you would deduce, approach to the proof of this that was due to Wigner is you calculate traces of powers of the matrix X by expanding in terms of the matrix elements. You use some combinatorial expansion, which might be Wick's theorem or something similar. As I say, actually, Wick's theorem, I think, is originally due to Isserlis in 1918, who I think wrote down the same thing, but Wick did that independently, and I think that's the common terminology for that expansion now. So you write down some combinatorial expansion, then you identify the terms which dominate in the large matrix limit, and so you have some combinatorial sum to evaluate, and it happens you can evaluate those, and you can compute the moments of the semicircle distribution in that way. But just philosophically, it's interesting to point out that for the Gaussian ensembles, we have a completely independent method of computing the semicircle law. So in principle, this illustrates the general point I wanted to make, that one can actually evaluate combinatorial sums using random matrix theory. So by making the connection between a combinatorial sum and a random matrix average, if you know the answer to the combinatorial sum, you can compute the random matrix average, but there are many, many instances where one doesn't know the combinatorial sum a priori. One doesn't know how to count the terms that appear, but one does know the random matrix answer, and so that tells you how to evaluate the combinatorial sum. This would be an example. So I shall skip the Wishart matrices because I was going to talk about those, but I'll finish with a toy calculation to illustrate what I think I'm going to speak much more about tomorrow, which is that random matrix theory, for random matrix theory as a sort of broader subject, this is just the start of the subject. One's not primarily interested in the eigenvalue density per se, but one's interested much more in fluctuations around this density. So if we were to have a microscope and blow up a part of this picture, then on the scale of the mean eigenvalue separation, this wouldn't look like a smooth picture at all. Rather, this would be well, it's a histogram, so this would be some fluctuating curve, and one wants to understand the fluctuations around the semicircle law on the scale of the mean eigenvalue separation. And that's one of the great achievements of random matrix theory, to establish that, and that requires much more elaborate methods than are required just to get the mean density. So just to give a flavor for how this is going to go, I'm going to give a very famous classical calculation, which you can do for yourselves in a couple of minutes, just to build up some intuition. So the idea will be to look at 2 by 2 random matrices. So this is an example. So by GOE, I mean the Gaussian ensemble that's invariant under orthogonal transformations, and by GUE, I mean the Gaussian ensemble that's invariant under unitary transformations. So this is a sort of baby example to do, but I think it's instructive. So let's start with the GOE. If X is a 2 by 2 GOE matrix, well, we know it's symmetric, and we can always arrange for it to have trace 0 by subtracting off some diagonal terms. So without loss of generality, that's the most general 2 by 2 real symmetric matrix. So random matrix theory would say that you associate with this space of matrices a probability measure, which would be e to the minus, and then the convention is to be 1/4 trace x squared with the measure. So the quarter is a convention that some people use, and so this would be up to some normalization. So the actual normalized value would be 1 on 2 pi e to the minus 1/2 a squared plus b squared. Well, the eigenvalues of this matrix are straightforward to write down. They lie at plus or minus the square root of a squared plus b squared. So one can ask about the distribution of the eigenvalues in this case. So if we want to know, for example, what the probability is of an eigenvalue lying in some interval from x to x plus dx, divide by dx. this would be just a delta function, picking out when the eigenvalue x is positive, when the eigenvalue lies at x, and then we're to average over the matrix elements, the independent matrix elements, dA dB, with the measure. So this would be writing down the distribution of the eigenvalues. In this case, there's only one independent eigenvalue, because the other is its mirror symmetric partner, by expressing it in terms of an average over the matrix elements. Now, it's obvious that what one should do here is go to polar coordinates. This will sound like a trivial step. This is sound like I'm giving a sort of lecture to in first year undergraduate mathematics. But there's a particular reason I want to emphasize this. If you go to polar coordinates, this is obviously independent of the angle, and that is directly related to the independence of this ensemble with respect to orthogonal transformations, that is, with respect to rotations of the eigenvectors. So the angle dependence is trivial and integrates out just to be 2 pi. So one's simply left with the radial part, x minus r, e plus 1/4 r squared dr. But then one has the Jacobian of the transformation, which is r. And this is actually really important, because this then leads to the answer that this is just x e to the minus, go for, yeah, sorry, that should be a half there, x e to the minus a half x squared. So the eigenvalues as a function of x, first of all, they only get up to about square root 2 in size. So the eigenvalues don't go too far. And this is reminiscent of the semicircle law here. The eigenvalues don't get too far. They're restricted in their range by the probability measure. But also, and crucially, from the Jacobian of the transformation, the eigenvalues don't like to lie too close together. So they don't lie too close to 0. So the eigenvalues don't get too far, but they don't get too close to 0 either. The probability of being at position x vanishes as x tends to 0. And this is going to be a generic feature of random matrices that plays an extremely important part in the general theory. So I'll leave as an exercise a very straightforward one. For you to do yourselves, that for the Gaussian unitary ensemble, in the 2 by 2 case, so matrices are of the form A minus A, B plus IC, B minus IC. The eigenvalues, the measure is when normalized 1 on pi to 3 on 2, and then it's conventional to multiply by a factor of 2, a squared plus b squared plus c squared. That, in fact, it's not 1/2 here. It's just a convention. The eigenvalues are plus or minus the square root of a squared plus b squared plus c squared. So if you also work out the corresponding probability that the eigenvalue, positive eigenvalue, lies between x and x plus dx, this just turns out to be 4 over root pi x squared e to the minus x squared. So the crucial distinction is that rather than vanishing like x as x tends to 0, this vanishes like x squared. And that, again, will be a generic feature of random matrix calculations. There's a difference between the Gaussian orthogonal ensemble and the Gaussian unitary ensemble, and that difference, one of the ways that difference manifests itself is that the eigenvalues don't like to be too close together in both cases, but the order of vanishing differs in the two cases. In the first case, it's 1, and in this case, it's 2. And in both these examples, this factor comes from the Jacobian of the transformation from an integral over the matrix elements to an integral over the eigenvalues. And that, again, will be a generic feature that I'll illustrate, I'll say more about tomorrow. But I think that's probably an appropriate place for me to start.
Well, if not, then we can get ready for the group photo.